Welcome to our presentation on next-generation energy sources, specifically on hydrogen fuel cells. In this presentation, we will first outline the basics of hydrogen power, going over the sources of hydrogen and how a hydrogen infrastructure may be set up. We will then talk about various forms of hydrogen storage and their advantages over traditional storage systems. We will then examine the electrochemical and thermodynamic concepts governing hydrogen fuel cells, before finally listing the advantages and limitations of a hydrogen fuel cell storage system in comparison to modern systems. Energy from hydrogen power is obtained through combustion of hydrogen, shown in equation 1 on screen. The hydrogen used for this may come from various sources, though the traditional source is from the steam reformation reaction and the accompanying shift reaction, shown as equations 2 and 3 on screen. It should be noted that since these do still produce some harmful byproducts, that other methods have been considered for sourcing hydrogen, such as biomass or direct production from electrolysis of water. We see, though, that the combustion overall does still give a negative value of its Gibbs free energy, indicating that it is certainly a viable source. When it comes to hydrogen storage, traditionally it has always been stored in the liquid or gas phase. However, as you can imagine, this is highly unsuitable for various uses of a hydrogen fuel cell system due to hydrogen's volatility. As such, new materials are required to allow for safer, more effective storage. These materials will additionally allow for greater energy density storage. Storage alloys such as AB2 and organic alloys have shown good potential in terms of the high energy density storage. Additionally, other storage types such as hydrogen like ammonia, have also shown good potential in proton exchange membranes due to their high mass fraction allowing for greater exchange. Carbon nitride storage systems have also shown a similar effect. Hydrogen fuel cells do have many advantages over traditional fuel sources. The primary advantage is that hydrogen as a fuel source produces none of the harmful greenhouse gases of fossil fuel combustion, thus reducing impact on global warming. Fuel cells additionally have been shown to outperform other alternative fuel sources in areas such as the previously mentioned energy density storage. Plus, it also has a far better charge time compared to its primary rival in electric power. This even allows it to be applied to sectors that electrical power cannot due to range limitations. We'll discuss more advantages of fuel cells as a power source later on. We will now discuss the electrochemical and thermodynamic chemistry behind the hydrogen fuel cell, which is what is responsible for their advantages in power and efficiency. The hydrogen fuel cell functions similarly to a traditional redox cell, the half equations for the cell being shown on screen as equations 4 and 5. Taking the standard definition for the Gibbs free energy shown on screen in equation 6, it is possible to extend this to determine the free energy of a cell using equation 7, in which the change in reaction Gibbs energy is equal to the number of half equations times the Faraday constant times the electrochemical potential of the cell. Rearranging to get the electrochemical potential gives a value of 1.23 volts, a strong potential difference between the two halves of the fuel cell. An important electrochemical factor is with regard to the charge and discharge cycles of a high fuel cell. This refers to the length of time required to fully charge the cell and the time for which it may produce energy, fully discharge. These cycles are important since they determine the longevity and potential degradation of the fuel cell, a key factor in its operational efficiency. The efficiency of a fuel cell may be determined by the work done by the system, equation 9, as well as by the heat taken in by the system and the waste heat, see equation 10. This efficiency has been shown to exceed that of traditional Carnot engine systems, and while still less efficient than electrical systems, say carbon paper electrode materials in hydrogen vanadium fuel cells may yet achieve even higher efficiencies.
As we know, hydrogen fuel cells are used to generate electricity. This is accomplished by converting chemical energy into electrical energy, which is then exhibited as cell potential and electrical current output. The equation for this conversion is hydrogen, which is the fuel, plus oxygen, which is the oxygen to produce water as the product. As you can see, there's a W and a Q in the equation, and so the W denotes the rate of electrical work done, and the Q denotes the rate of the heat transfer into the system from the surroundings at a constant pressure and temperature. Using this, we can use the formula or the equation W equals EI delta T, where E is the cell voltage, I is the current, and delta T is the amount of electricity transferred. In a fuel cell, electrons flow from the anode to the cathode, generating a current. As such, the electrical work here can be calculated as work done equals negative N times Faraday's constant times the cell voltage, where N denotes the number of electrons transferred, and the Faraday's constant in this case is 96,493 coulombs. With this, we can start to work out the Gibbs free energy. And so the Gibbs free energy is the maximum amount of work done on the system. This is shown by WEL equals delta G. So we can substitute W for delta G to get delta G equals minus N FV cell. If we make the E cell the subject of the formula, or in this case E rev, we get E rev equals negative delta G over NF. In this case, E cell becomes E rev as the highest possible electrical energy output, and the corresponding electrical potential differences between the anode and the cathode are achieved when the cell is operated under thermodynamically reversible conditions. Using hydrogen as an energy source has many benefits. One such benefit is that it has a very high energy density of 141 joules per kilogram, compared to that of coal, which is a very commonly used energy source, which only has 30 joules per kilogram of energy. This means hydrogen is nearly 5 times as energy rich, and so it's more efficient to use hydrogen as an energy source than it is to burn coal. Hydrogen also has an energy reservoir factor of 1, meaning it's easier to store when energy usage is low and in times of surplus energy, and it's easier to use when energy usage is high to support the demands. A combustion formula doesn't include carbon at all, so the generation of the electricity itself from the hydrogen is completely carbon neutral. However, the infrastructure required to convert the chemical energy to the electrical energy will most likely have a carbon footprint. It can be transported safely via pipelines along long distances. It is non-toxic. It can be acquired in a multitude of ways, for example, electrolysis. This also includes from renewable sources, such as from biodiesel. It can also be stored for relatively long periods of time and stored for way longer than electricity or heat can. And it's a relatively new technology, meaning there'll be improvements to it in the future, and so the efficiency of it will improve over time, and it'll become a better energy resource.
The advantages to hydrogen power, it also still possesses some major drawbacks. One of these is the ongoing investigation into how they may be adversely affected by external factors, since they may be affected more so than traditional fuel storage sources with regard to things such as degradation. Considering hydrogen efficiency, say, whilst their efficiency is acceptable, it is still not as good as it could be. The use of SOFC systems combine hydrogen cells with other fuel sources, however, this does bring its own issues, see figure 9 on the screen. Hydrogen fuel cells may also become more efficient through the use of fuel cell stacking. However, this has proven difficult to achieve as whilst new technologies are being developed, they have yet to be fully tested and implemented. However, perhaps the biggest issue with regard to fuel cell is the limits on the hydrogen economy that supports them. Primarily the fact that steam reformation and shift reactions are still the most viable method of hydrogen production. And whilst ways of increasing the efficiency of other methods, such as use of photovoltaics in the hydrogen electrolysis, have been examined, they have yet to be made economically viable.
So to conclude, um, it generates electricity via the transfer of electrons from the anode to the cathode. Hydrogen fuel cells will be important for moving away from non-renewable and polluting sources of energy, um, because the hydrogen can be generated via renewable sources, although that's not the most efficient way, it can be done by that. It's quite effective, shown by the high energy density, and it's much less of a threat to the environment compared to other energy sources due to it not containing or not having a carbon footprint. It's not optimized, so there are improvements to be made, meaning it will get better in the future. However, it's more likely to be subject to external influences such as the climate than other fuel cells. Um, SOFCs can have their own issues, um, one of which includes sulfur poisoning. And the only economically viable ways to generate hydrogen right now are from steam reformation and shift reactions, which release carbon monoxide and carbon dioxide, and so are not very favourable reactions.